Hey everyone, I hope you're doing well. In this video, I'm just going to be going over an answer key for the Unit 5 Homework 3, which is dealing with unit prices, how to find them, using unit rates, as well as determining a better value between two different types of options using unit rates. Then I'll go into having some practice problems with graphing rates and ratios, seeing how they're related to linear equations, and then finishing up the video, I'll be working with unit conversions, how to use conversion factors to convert some units to a different type of units. And I'll go over some enrichment problems as well, dealing with proportions, which is just another application of rates and ratios. So yeah, let's get right into it here. So let's look at number 1. In part 1, we're going to determine the unit price by writing rates first. So for number 1, it says Jack bought 8 pencils for $2.24. So I'll take the $2.24, and that's for 8 pencils. And to find the unit price, we just have to find out the price of 1 pencil. And to do that, we'll divide top and bottom both by 8. So we get the price for 1 pencil. And if we were going to take 224 and divide that by 8, I'll do that on the side here. I'll do that in gray, 224, because it's not very different than the other color. So 0 point. This is 216. This will be 4, 5, 6. Bring down the 4. It's an 8. Okay, so this is going to be 64 cents. Oh, oops, not 64. This is going to be 0. So, excuse me, that's going to be 0.20 or 28 cents per 1 pencil. So I'm just going to write that here. This is going to be, whoops, this is going to be 0.28. It's 28 cents per 1 pencil. And that will be the answer for this first question. Okay. So number 1, all done. Number 2, it says Milo bought 5 used books for $9.65. So writing that as a rate, we can say that's going to be $9.65. That's for 5 books. So what do we think here for the unit rate? We can divide this by 5, divide this by 5. So this is kind of nice. It'll go in evenly because it ends in 5. That's going to be a 1. And again, this is just a little bit of long division. So hopefully you'll feel more comfortable getting practice here. That's $1. Have a remainder of 4. Bring down to 6. $1.90 something. $1.90. That's a 1. That's a 5. $1.93. Yeah, this goes in evenly. So final answer here. If Milo buys 5 used books for $9.65, then this is going to be $1.93 for 1 book, or per 1 book. That's the unit price. The price of just one of these things. Okay. Number 2, all done. Number 3, Lulu bought half of a gallon of apple juice for $2.47. Oh, actually, I forgot to write $1.93 up here, so I'll go ahead and write that in. For this one, though, we know the price is $2.47, and that's for half of a gallon. Now, I showed this a little bit in the YouTube video before on how to go about this, but I think the easiest way or the fastest way is we need to get 1 on the bottom, right? So in order to do that, we could just multiply a half by 2, and that'll get you the 1. So I think the quickest way or most efficient way to solve this would be to multiply by 2. And you could go ahead and divide by half, but you'll see that dividing by half is the same thing or equivalent as multiplying by 2. 8, 9, I think 4.94 is what I'm getting. $4.94. That will be the price of 1 gallon. It should be double the price because you're only getting half a gallon there. Oops, what am I doing? Okay, so where can I write this answer? Maybe I'll move this up a little bit. And I'll move these out of the way as well, just to create a little bit more space. Okay, so I'll say here that this is going to be $4.94 for 1 gallon, or per 1 gallon of apple juice. Okay, next one, number 3 is done. Miss Jager bought 36 packs of fruit snacks for $31.68. So how can we write this as a rate first? Well, as a rate, this would be $31.68. That's for 36 packs. So if we want to find the price of 1 pack, then we'll have to divide the bottom by 36 and the top by 36, right? So really, what's the problem we have to do here? Long division is just going to be 31.68 divided by 36. Well, it's going to be less than $1, right? Because 36 doesn't fit into 31. 36 into 316 though. We know 36 times 10 is 360. So what's 36 times 9? It's going to be 54, carry the 5. That's 27 plus 5. Oh darn, is that still too big? I guess I should have known that, but oh well. I'll just go ahead and do another one. Not hard, just kind of time consuming. That's going to be 48. That's a 4. 24, 28, 288. That will fit. So we'll put an 8 here. That's going to be 288. Let's see if I can do this correctly. That's going to be an 8. And then I think this is just a 2. Oh yeah, it's another 8. So 8 times 36 is another 288. And that's a 0. So I'm going to say this is going to be 88 cents for 1 pack. That makes sense because if it costs $36 for 36 packs, then they're all $1, but you get more than, or it costs less than $36, so it should be cheaper, right? So it's going to be 88 cents for 1 pack. Oops, 88 cents per 1 pack. I'll just put that right here. And that is the answer for number 4. And there you go. Part 1 is now done. Okay, let's move on down to part 2. Okay, so we're going to see if we can find the better value between these types of deals. So we have this first one, number 5. 1 pound of chicken nuggets is going to cost $2.15, or chicken nuggies, as we might say, or 3 pounds of chicken nuggies for $5.76. So to do number 5, I don't know where I'm going to put this work actually. I'll just put it down here. We have option A, and that's going to be $2.15 for 1 pound. And then we have option B, and that's going to be $5.76 for 3 pounds. So the one on the left is already good to go. It's already a unit rate, so we don't have to deal with that one. But the one on the right, we should get the unit rate. And to get per 1 pound, to compare these, we should divide 576 by 3, right? So if we do 576 divided by 3, it's going to go in 1 time. It's 3, it's 2, 190, 192, because it's a 6, right? $1.92, 6 and a 0. So okay, we have $1.92, 1.92. So comparing these two things of we have $2.15 per pound and we have $1.92 per pound. So when we're trying to see which one is the better deal, you guys should choose this one here. 3 pounds of chicken nuggies for $5.76. This one's the better deal. Okay, and the proof behind that is $1.92 per pound is definitely cheaper than $2.15 per pound. Okay, so that is number 5. Actually, I'm going to go ahead and try something new and do a little bit of split screen here so I can see the problems. And now I have some more space to actually write on a piece of paper or on my iPad. So for number 6, if we take a look here, we're going to compare 5 ounces. I'll go back to this. 5 ounces for $6.95, or we're going to buy 14 ounces of juice for $19.60. So let's go ahead and take a look at those options. And write down those two as rates, right? So if we have option number 1, that is going to be $6.95, and that's for 5 ounces. And then for option 2, we have $19.60, and that is going to be for 14 ounces, right? So I guess making this a little bit easier to see for myself, I'll put this as over 1, put this over 1 to get the unit rate. This one we'll have to divide by 5 and divide by 5. And we know this one we'll have to divide by 14 and divide this one by 14. Okay, so really the only work we have to do for option 1 is we're going to take this $6.95, we'll divide that by 5. It's going to go in once. It's a 5, it's a 1. $1, it's a 3, right, for 15. It's a 4, bring down the 5. That's going to be a 9. That goes in nicely. Okay, so for option 1, this is a $1.39 for 1 pound of this juice. Or sorry, is it ounce? No, ounces of juice, okay? So that's gonna be our unit rate. Now for option number 2, we can go ahead and see, okay, if we have $19.60 and divide that by 14, well, it's gonna be $1 something because 14 fits into 19 at least once, right? Or exactly once with some left over. This remainder should be 5, bring down this 6. Oh, okay, I think 14 times 4 is exactly 56. I'm getting 0. Oh, is that right? Yeah, $1.40. Okay, so we have $1.40 for 1 ounce. So if we take a look at the left one, $6.95 for 5, divide that by 5, that was $1.39. And for one on the right, we have $19.60 divided by 14, and that was $1.40. So basically comparing these two unit rates per 1 ounce, I think we know which one is a slightly better deal. We're gonna have to go with option 1 here, right? So going back for our answer key, we can see that option 1, the 5 ounces for $6.95 is going to be the better deal. Okay, so I'll post both PDFs to this online just so you can see all of the work written out, but this is what we got so far. Okay, while we're still over here, let's take a look at number 7, a 12-ounce box of macaroni and cheese. That's $2.15, and then a 16-ounce box of mac and cheese that costs $2.88. Okay, so this is number 7. We'll go back over here, scroll down a little bit, and number 7. Well, we got 2 options, right? Option number 1, it's definitely easier to write with a bigger screen here. Option number 1, we have $2.15, and that is going to be for 12 ounces, and we'll find the unit rate. And then option number 2, is this a bigger box? Yeah, bigger box, 16 ounces, but it's $2.88. So $2.88, that's for 16 ounces. We want to find that per 1. So hopefully you're getting the hang of this, but you'll divide by 12 and 12 on top and bottom, and divide by 16 and 16 top and bottom to get the unit rates. Here we just have some long division once again. So $2.15 divided by 12. It's going to go in 0 times here, so we know that's going to be less than $1 at this point, right? And this is going to go in just 1 time. That's going to be 12. That's 8 and 9 is a remainder. 5 comes down. I think this is going to be a 7. 7 times 12 is 84. Yeah, 8 would be 96, so that's too much. It's going to be 11 off. And we need to round to the pennies place, so we definitely need another value here. So again, we can always add a 0 inside the house, bring it down. And this should be a 9. And so this is going to be, I think, 108, if I'm correct. I think so, yeah. And so this, just keep in mind when you're dealing with rounding that you need the pennies, that's where the 7 is. And this 9 is saying we actually pretty much have 18 cents here. So this is going to be 18 cents, but just keep in mind it's slightly less than 18 cents, right? So this is actually approximately equal to this value. It's a little less than 18 cents technically, okay? If we look at the one on the right, option number 2, we take our $2.88 and divide that by 16. This is less than $1 as well. 1 times 16 is 16. We're left with a 12, and bring down the 8 here. And how many times does 16 go into 128? I'm thinking probably something like 8. I think that's exactly right. Yeah, 8. 8 times 16 is 128. And if you weren't sure, just multiply it out and do some work on the side. But that's going to be exactly 18 cents per 1. What are we talking about? 1 ounce of mac and cheese. Okay. So we have our 2 unit rates, and while these look like they're identical, just keep in mind that the one on the left here is actually a little bit less than 18 cents, right? It's not actually 18 cents. So if you have to technically say which one's a better buy, you should say option 1. Slightly cheaper in the long run. It'll definitely end up being cheaper if you buy a lot of ounces, just because the fractions of pennies will end up creating less money than the full 18 cents per ounce. I know it's a little bit strange, but trust me, the unit price is slightly under, right? Not a big difference, but it's still mathematically a small difference. So we know the better deal here is going to be the 12-ounce box of mac and cheese, and that's for 15 or 12 for $2.15. Sorry. Okay. The next one we have here is we have 10 trading cards for $14.50, or 15 trading cards for $22.50. So we want to find out the better deal between these two. Maybe I'll just start on a new page so I don't have to move stuff around. For number 8, we have option number 1, and that is buying for $14.50. You can get 10 of these trading cards. To find the unit price, we'll get per one. For option number 2, let's see, we have $22.50. That's how much it costs for 15 trading cards. That's per one. Alrighty, and we'll divide this by 10, divide this by 10. That won't be too bad. Divide this by 15 and divide this one by 15. Okay, so just keep in mind whenever you're dividing a number by 10, we really just slide the decimal over one time to the left. So if you're dividing this by 10, you can just slide it over once this way. So dividing this by 10, this will end up being 1.450, which is just equal to $1.45. Okay, so that's just for one trading card. Now, if you didn't want to do it that way, right, and you wanted to show the entire long division, that's still doable. You're just going to notice that it's kind of silly after a while. This will be a 1, be a 10, it's a 4, and a 5. This is a 4, and this is a 40. It's a 5, 0. It's $1.45. So feel free to use that shortcut if it's helpful. Just slide the decimal over once to the left when you're dividing by 10, and that'll save you a little bit of time. Okay. For this next one, we have $22.50. We're going to divide that by 15. That's going to be 1, 15, 7, 5. 5 times 15 is exactly 75. It's a 0. That's a 0. $1.50. All right, so this is $1.50 per each of these trading cards. Comparing that to $1.45, I think we know the better buy here happens to be option 1, right? So going back over here, if I were to choose, actually buying the lesser amount of trading cards happens to be a better deal in this case, right? You have to make sure you're not always saying the one that's more is always better. It's not always the case. You have to make sure you're comparing the unit price per one of them. Okay, so at this point, that is part 2. Part 2 is now complete. Now we're going to take a look at part 1, or sorry, part 3. I should know part 3 comes after part 1 and 2. So rough line here. I know this one's a little bit disorganized compared to maybe some of the ones I've done in the past, so sorry about that. But just trying to make sure I'm showing all the steps out to help anybody that needs help with writing all this out. So for part 3, we'll start with number 9. We have to show, let's see what the problem is. You have to run 75 miles. You're running 75 miles in 15 weeks. We need to create our own table, create some ordered pairs, plot them on a coordinate plane, and show a linear relationship. Okay, so we'll do a bunch of things here. Hopefully this is going to make sense though. We are going to start off saying, okay, as a rate, I don't know why I'm putting a $ sign on. As a rate, this is going to be 75 miles in 15 weeks. All right. Remember, time is our independent variable, and their independent variable is always going to be per one of when we're doing a unit rate. So for 1 week, and I'll abbreviate as 1 week, WK, to get 1 week, we'll divide both top and bottom by 15. And I know 75 divided by 15 is equal to 5. So this is 5 miles per week, right? So it's maybe not as bad as you might have thought it was. It is a lot of miles, but across 15 weeks, running 5 miles a week, I don't know, you could run 1 mile a day for 5 days. And that's not too many miles, I don't think. If you're training for a 5K or something like that. Maybe it's a lot of miles if you're a sprinter or you don't like running at all. So 5 miles per week is our unit rate. That's what this is right here. This is our unit rate. And what you can do with that is you can actually, make an equation. You can make a table. Maybe I'll say for the miles, we'll just say this is M, and for the weeks, we'll do T for time. So we could write a linear equation and say the number of miles you run depends on how many weeks go by. And you're running 5 miles per week. So you can say M is equal to 5T. This right here would be our linear equation. All right, so if you're doing something at a constant rate, it's not going to change. So every time you run another week, or you run for another week, you'll end up running 5 more miles. So if t is 1, you get 5 miles. If t is 3, you get 15 miles. If t is 15, you get 75 miles, which is what we started off with. But that's the linear equation. Okay, so the unit rate helps us find out that coefficient of 5 in front of the t. We then need to create some sort of table. So time is our independent variable, and number of miles is our dependent variable, right? The more time that goes by, the more miles you can run. If you run 1 mile, we know if you run for 1 week, that's 5 miles. For 2 weeks, that would be 10 miles. For 3 weeks, that would be 15. For 4, that would be 20. Again, every extra week, you can run 5 more miles, right? That's the goal here. So I'll just go to 5. I think that's enough. We can keep going up to 75, but I think you hopefully get the point at this time. Some ordered pairs we can say here. Well, this is really just saying 1, 5. At 1 week, that's 5 miles. This is really just saying 2, 10, and so on and so forth for the rest of these values in the table. Okay, so going a little bit further, I'm not going to draw things too precisely this time. 1, 2, 3, 4, and 5. And then we could say something like 5, 10, 15, 20, and 25. So again, just skip counting differently. Just stay consistent along your x-axis, which is t, and our y-axis, which is m. Perfectly good. And our ordered pairs, because we're scaling them the same for each one of these, like kind of saying one box ends up being, or one tick mark ends up being what we're looking for, this ends up being a lot nicer. So I know this is not the cleanest looking graph, but if I had some graph paper, I guess I could make this look a lot nicer. Okay, so this would be a graph, and you should label this. This is going to be number of weeks, and that goes along the x-axis. And this is the number of, these are the number of miles going along the y-axis. And you should put it some sort of title. I don't know, I can say training for something. Maybe you're just trying to get in better shape, or you have a goal, but you have a nice title. But I think this would be a pretty full answer for number 9. Using the unit rate, you're noticing that for every 1 week that goes by, right? For every 1 week that goes by, you run 5 more miles. 1 more week that goes by, 5 more miles. 1 more week, 5 more miles. 1 more week, 5 more miles. That's kind of the idea here. If no weeks go by, you run no miles. Okay, and we could continue this graph until we got to 75 miles in 15 weeks, but this is just a linear relationship, or the linear equation for this constant rate of change. Okay, so that's number 9. Let's take a look back over at the problems. Number 9 is all good to go. Let's look at number 10. Miss Carsdale makes 36 baskets in 9 minutes. So let's just do the whole thing over again, but we have a different rate. So 36 baskets in 9 minutes. So this is number 10. How did I go about doing this? Okay, so I might refer back to that, but it's 36 baskets. Maybe I'll write B for baskets in 9 minutes. So maybe I'll use M there for the minutes. I can write that nicer. And to find the unit rate here, you need to find for 1 minute. I'm not going to write out the word minute here, but if I divide by 9 and divide by 9, we can see here that 36 divided by 9 is just 4. So this will be our unit rate. I think these are the same colors I used, I'm not sure. Unit rate. So if the unit rate is 4 baskets per 1 minute, the baskets depends on the minutes, right? So the baskets, we can say, is depending on the minutes. Our unit rate is our coefficient. So it's per 4 per minute, right? Every minute she's going 4 more baskets in maybe basketball. So this is our linear equation. All right, and just keep in mind that the independent variable is typically going to be time, right? So the time times the rate, or the unit rate, is going to equal the dependent variable. So the baskets depend on how much time she has. I'd assume that if she had more time, she could make more baskets. If she had less time, she could make less baskets. So the baskets depend on the amount of time she has. Okay, so going ahead and making a table, minutes is our independent variable, baskets depends on it, and making a quick little sketch of the table. 1, 2, 3, 4, 5 is good. Let's just say for 5 minutes, 1 minute, that's 4 baskets. 2 minutes is 8 baskets. 3 is 12. 4 is 16. 5 is 20. Okay, so we have a bunch of ordered pairs here. So here's 1 comma 4. Here's 5 comma 20. These are examples of ordered pairs. And we can then go ahead and make a graph, right? Maybe something like this. Minutes, baskets, 1, 2, 3, 4, 5. Label those in. And then we can say 2, 3, 4, 5. I'll put in 8, 4, 8, 12, 16, 20. This is number of minutes. I'll put that along the x-axis. And this is the number of baskets. I'll put that along the y-axis. And I'm going to label this baller, because why not? 1, 4, 2, 8, 3, 12. This is definitely easier if you have graph paper. And you would draw something that looks like this. Okay, so there we have number 10. Oops, number 10 is now done. Okay, so let's look at number 11. Mr. Lanzetta's car uses 5 gallons of gasoline for every 120 miles that it travels. So let's go over to paper here. Down number 11. And so the rate here is it's going to be 120 miles for every 5 gallons. So I'll put the miles on top, and that's for 5 gallons. I'll put 5 GAL on the bottom. And to find the unit rate here, we're really going to have to find it for 1 gallon. How far can you go in with 1 gallon of gas? And that's typically how cars are, sort of advertised as to like how many miles per gallon, how many MPGs they get. 120 divided by 5, that ends up being 24. So this is 24 miles per 1 gallon of gasoline. Maybe not so great, but if you go back 5-10 years, that's probably a little bit more common with cars. And let's take a look. So this is going to be our unit rate. This is unit rate. What would our equation be here? Well, maybe we can use the variable M for miles, and we can use G for gallons, and we can say the number of miles depends on the amount of gallons you have, but we do know that you get 24 miles for every gallon, right? So if you had 1 gallon, if G was equal to 1, 24 times 1 is 24, you could go 24 miles. If G was 2, you had 2 gallons of gas, then 24 times 2 is 48, you could travel for 48 miles. So this right here would be our linear equation, right? Our linear equation. If it's a linear equation, we know we can make a table, we can make a graph, so that's exactly what I will do now. If we say we have the gallons, which is the independent variable, and then we have the miles, which is how many miles we can travel, I'll just go ahead and make our table of 1, 2, 3, 4, and 5 gallons. Then if we have 1 gallon, that'll be 24, 2 gallons is 48, 3 gallons, 72, 4 gallons, 96, 5 gallons, 120, which is the rate that we were originally given, okay? If you're wanting to look at some ordered pairs, here's an example, 2 comma 48, that's an ordered pair. Something like 4 comma 96, that's also a nice ordered pair you could use. And going ahead and making a linear graph, we'll need quadrant 1. Don't worry about quadrants 2, 3, or 4, since we can't really travel negative miles or have negative gallons. Our gasoline is going to be our independent variable, and the miles is dependent. We'll go to 1, 2, 3, 4, 5, 3, 4, 5, and we'll go to make 5 tick marks here. 3, 4, 5, 24, 48, 72, 96, and 120. Alrighty. So going ahead, we can plot these points. Again, it would be much steeper if every scale was the same, like the x-axis and y-axis went by ones or went by equivalent amounts. But since we're going by ones along the x-axis and going by 24s along the y-axis, it looks the same steepness as every other graph I've done here. Along the x-axis here, this is the number of gallons of gasoline, just labeling that up. Going along the y-axis, this is going to be the number of miles going along the y-axis. And for a title here, I don't know, we could call this road trip maybe. If you're driving 120 miles, you're going pretty far somewhere. Okay, fairly far at least. And so here's our linear graph, okay? Something I just kind of want to go back and mention is, what about our independent and dependent variables? For number 9, the weeks was our independent variable, all right, IV for short, and the number of miles was going to be our dependent variable, DV for short. For this problem here, for number 10, the minutes was going to be our independent variable, and the number of baskets depended on that, and that's our DV. Moving on here, the number of gallons in number 11, that was the independent variable, and how far you can drive depends on how much gasoline you have in your car. So those are the independent and dependent variables for 9, 10, and 11. Okay, so number 11 is now complete, okay? And we can now move on to part 4. So part 4 is talking about equivalent measurement using conversion factors, right? So if you haven't watched that video, check out the video on conversion factors. You can use a reference sheet. You can also look them up online using any resources you can find if you don't know your conversion factors. All right. So let's take a look at number 12, where we have 39 feet and we want to convert that to yards. Okay. So this is number 12. Start a new page. Number 12, we have 39 feet and we want to convert that to a certain amount of yards. Okay. YDS for yards. And so if we want to convert that, you start off by writing 39 feet as 39 feet over 1. Anything over 1 stays the same. And a conversion factor you want to know here, use conversion factor, same color as before, then this is going to be, well, there are in 1 yard that is equal to 3 feet, right? Now just keep in mind that you want to put the feet on bottom so that we can cross cancel the units. Feet and feet are going to cross cancel. And then when you go ahead and multiply, 39 times 1 on top is going to be 39 yards, and 1 times 3 on bottom is just 3. And this just simplifies down. 39 divided by 3 is equal to 13. So it's going to be 13 yards for number 12. Okay, that's if we have 39 feet, that would equal 13 yards. Okay, that's number 12. Let's look at number 13. It looks like we have 13 pints, and we have to convert that to quarts. Well, let's see, for number 13, we have 13 and 13. 13 pints. We want to convert that to quarts. Okay, see how many quarts there are going to be. Well, the 13 pints, just like the last problem, I'll abbreviate PTS for pints. That's going to be over 1. And the conversion factor, if you weren't aware, again, you could look this up. There are 2 pints for every quart. And I only really know that because I've worked in an ice cream store and we sell pints and quarts. So we know there are 2 pints for every 1 quart, 1 QT. Very cute. The pints will cross cancel, and we will have 13 times 1 on top is 13 quarts. And on the bottom, 1 times 2 is 2. 13 divided by 2 is 6.5 or 6.5 quarts. So if you have 13 pints of ice cream, that's the same thing as 6.5 quarts of ice cream. Okay. If you're wondering what a pint looks like, if you've had like a pint of Ben & Jerry's, you might have an idea of what I'm talking about. Number 14, if you go 1.5 miles in, we have to convert that into yards. Well, we probably need to look up what that is going to be. I could probably find it out pretty quickly. If you aren't aware, 1.5 miles, we need to turn that into yards. Figure out what that is. So 1.5 miles, 1.5, put MI for miles, put that over 1. And I'm going to go ahead and look this up. 1.5 miles, how many yards? I don't have it memorized, so 1 mile in yards. Okay, after a quick search, 1,760. So we want this to be, we want miles on bottom, so I'll put 1 mile on bottom and then put 1,760 yards on top. And the reason why we want to put these particularly on top and bottom is so that the miles will cross cancel. And on top, we have to do 1.5 times 1,760. 1.5 times 1,760. Half of that's 850, 880 plus that. Okay, that's about 2,640. I think it's exactly 2,640 yards over 1, which is just 2,640 yards. Okay, so if you go 1.5 miles, that is 2,640 yards. Okay, so popping on back over here. Number 14 is now done. Let's take a look at 15. We have 4.5 pounds and we want to convert that to ounces. So what do we do first? Well, writing it down for number 15, we have 4.5 pounds and we want to convert that into some amount of ounces. And I'll just show you the abbreviation is OZ for ounces, a little bit weird. And writing the pounds, let's write 4.5, that's LBS as an abbreviation. And we're going to multiply that by, well, I know there's 16 pounds in an ounce. So let's turn the 16, we'll put the 16 ounces on top and 1 pound on bottom. And again, we'll do that so that we can cross cancel the pounds and turn it completely into ounces. And 4.5 times 16, well, 4 times 16 is 64 plus another 8, that's going to be 72. So it's 72 ounces per one. And so this is just 72 ounces. Remember, OZ stands for ounces. Okay, so those, if you have 4.5 pounds of something, that would be the equivalent when you're talking about ounces. This next one, we have 0.25 miles, and we want to convert that to feet. So let's go ahead and give that a try. This is number 16. So 0.25 miles, it's MI, and we want to convert that to feet. Alrighty, so put a question mark there. And just same thing as usual. Don't be too alarmed with the decimal here. We'll put that over 1. And what's the conversion factor? Well, I think I have this one memorized. For 1 mile, there are 5,280 feet. 5,280 feet. And the reason why we put the miles on bottom is so they cross cancel and we're just left with feet. That's the only units we have left. And if we have 0.25, that's 1/4 of 5,280. I think that will be, if you take a fourth of that, 1,250 plus another 70, or 1,200. Yeah, I think this is going to be 1,320. So 1,320 feet over 1. 1,320 feet would be 1/4 mile. Okay, and just check that one more time. If I multiply 0.25, that's 1/4, 5,280. 1/4 of 52 is 13, and 1/4 of 80 is 20, so 1,320. That makes sense, yeah. So always like just double checking. 16 is now done. Number 17, we're going to convert inches to feet. Okay, so let's see here. For inches to feet, I'll take the 85 inches. Oh, oops, and then we're going to convert that to feet. And we convert that 85 inches over 1. Hopefully that's getting a little bit more comfortable. And how many inches are there in a foot? Well, I think there's 12, right? So 12 inches, we'll put that on bottom, and 1 foot on top. And we will cross cancel gladly. And we really have 85 over 12. I think they're, can't divide them by anything in particular. 85 divided by 12. I think it's going to be nothing really nice here. So we can just write, how many times does 12 fit into 85? Well, it fits in 7 times 84. So it's 7 and 1/12. All right, so 7 and 1/12. So 7 times 12 is 84 with 1 left over, over 1. So if you have 85 inches, that would be, if you were 85 inches tall, that would be quite tall. You'd be 7 foot 1 inch because there are 12 inches in a foot. So same thing as our equivalent, 7 foot 1, as you would say here. Okay, you might say. So that's 17. Okay, so that completes all of this homework assignment for what you are required to do. But I'm just going to do a few questions from part 5 just in case anybody is interested in seeing how some of them are done. So maybe I'll take a look at number 16 and I'll just run through a couple problems here just to give you an understanding of how to do these types of problems. So let's see. I'll start with number 16. I know the numbers are off, so sorry about that if that's confusing, but these are just the ones I chose. So part 5, enrichment. Number 16, for what it's worth, is labeled there. 140 to 56, that's a ratio, is equal to x minus 1 over 14. Okay, so we have a ratio on the left, and it has to somehow equal the ratio on the right. So to get from 56 to 14, right, or from 14 to 56, to get from here to here, we'd have to multiply 14 by 4. okay? And to get from x minus 1 to get to 140, you'd have to multiply that by 4 as well, right? So the bottom has to equal the bottom by multiplying by 4, and the top has to multiply 4 to get to the top. That has to stay consistent. So if we go ahead a little bit, if the bottoms match, then we then have to say that if you take the x minus 1 and you multiply that by 4, that equals 140, right? If 14 times 4 is equal to 56 on the bottom, then 4 times the quantity of x minus 1 does equal 140. So using a little bit of distributive property here, this is one way we can do it. We'll get 4x minus 4 is equal to 140. Now this is just a two-step equation. We can add 4 to both sides. By adding 4 to both sides, we can say 4x plus 0, which I won't write, is equal to 144. Using the identity property, and then using the division property of equality, we can divide both sides by 4 and say x is equal to, I think that's equal to 24. That should be right. Let me just check real quick. No, 36. Half of 144 is 72. Half of that, so yeah, 36. So x equals 36 here. All right. If you wanted to check this, you're totally welcome to plug this in right here. That would be 36 minus 1 is 35. 35, I'll just check it right here. 140 to 56 equals, if this was 35 over 14, yeah, if you multiply this by 4 and multiply this by 4, you would get 140 and 56. So x does equal 36. Okay, so 16 is now done. Try a couple more problems. Let's try 17. We have 40 over 84 is equal to 70 over x plus 7. Okay, so this one's a little bit trickier just because 40 doesn't go into 70 evenly. And we could use a fraction, but if I can avoid that, I will. But 80 has to get to this value the same way. So let me see here. I think we could divide this both by 4. That's a common factor. And if we divide them both by 4, we'll get 10 over 21, I believe, is equal to 70 over x plus 7. Remember, in isolation, we can take a look at any fraction or ratio and simplify it down. So that's the same thing. And the reason why this is more useful is because then you can now see 10 times 7 is 70. So 21 times 7 is going to be equal to x plus 7 on the bottom. So we can now go ahead and say, I'll go back to using the same color. We can go ahead and say on the bottom that 21 times 7, 21 times 7 is equal to x plus 7. Okay, 20 times 7 is 140, 7 times 1 is 7, so that's going to be 147 is equal to x plus 7. And solving this as a one-step equation, we can use the subtraction property of equality and say that x is equal to 140. Okay, you can plug this in into the equation above, right? You could take this, plug it in, but I promise you this does work out nicely. 147, yeah, that seems right. Another way to think about this is 84 is a little bit more than double of the numerator, right? If you double 40, that's 80, but 84 is a little bigger. If you double 70, that's 140, but we actually get 147 when you add these two numbers up, and it should be a little bit more than double of the numerator, so that seems to check out. So for number 17, that one is good to go now. Maybe I'll just try one more problem from this enrichment section, because I think once you see a couple of them, the rest of them end up being quite similar. You just have to use different values. So 42 over 24 is equal to x plus 11 over 52. Scroll up to give myself some more room. And if we think about this, I don't know, 24 doesn't go into this evenly. I'm sure we could use a fraction or decimal, but I'm going to prefer to see if we can simplify this a little bit. I think we can divide these both by 6, right? Yeah, dividing them both by 6. 42 divided by 6 is 7. 24 divided by 6 is 4. Is equal to x plus 11 over 52. Looks like I picked the GCF, which is helpful. 4 to 52, well, there's 52 cards in a deck, and there's 4 suits, and there's 13 of each one, so I know 4 times 13 is 52. That means 7 times 13, we can write this as an equation. 7 times 13 is equal to x plus 11. 7 times 13 is 91, so we can say 91 is equal to x plus 11. Then we can use the subtraction property of equality, take away 11 from both sides, and say x is equal to 80. That should be our final solution for number 18. Okay, so if we, hopefully this was helpful in just giving you a slight glimpse into some of these more enrichment type questions. I promise you the rest of these all work similarly. Some of them have fractions and decimals in them, and you can just use your understanding of how you would do that. You might need to use some long division or some standard algorithm for multiplication in there, or you can use a calculator if you're feeling like you don't want to write out all that work. And there's also one application question. I'm not actually going to go through that one right now, but it uses your understanding. There's more, I guess, decimals in these ones, but this one's the same idea, just working with fractions. If you'd like to see, me go through something like 28, you can ask in class, or you can comment down below, and I can also try to get to making a tutorial or a little like overview answer key of that problem as well. Okay. Hopefully this was helpful, and keep up the good work, everybody. Hopefully I will see you all soon. Okay, bye.